Okay, good morning, everyone. Good morning. End of week 9. It's like the final 2K of a marathon. End is in sight. Okay, so on Wednesday, we didn't get time to finish everything about the disease models, so I'm just going to finish off the last problem from Wednesday before moving on to stuff about competition models. So we talked about the general SIR model, or a general SIR model, and we looked at what happens if we have specific parameters in that model, and we saw that we ended up with an endemic equilibrium is a stable spiral. And what that actually means biologically is that we have these epidemic waves. So we have the first wave, and then because immunity wanes, we end up having a second wave, and then the cycle repeats. But each of those waves gets smaller and smaller until we tend towards a stable level of disease in the population. So now we're just going to look through a general stability criterion. So rather than having specific parameter values for our A, K, B, and C, we are going to have just those as general parameters, okay? And what we want to do to understand whether an epidemic will take off or not is look at what happens if we have a population. I don't know what is going on with the screen there. That's kind of weird. Okay, I don't know what, it looks fine on my iPad, but apparently it doesn't look fine on that. We're going to look at what happens when the population is almost entirely susceptible. So we're going to have this S is going to be approximately equal to N. We're going to see if there's a tiny amount of infection in the population, whether that can take off and we have an epidemic or not. This is obviously really important if you're doing something like public health modeling to understand whether an epidemic is going to take off. So what we're doing essentially is we're going to look at the stability of this system at our disease-free equilibrium. In this model, I'll just tell you it's N0. So that's when everyone in the population is susceptible and no one's infected. If this is stable, then that means that our infection is just going to die out because we move a little bit away from it, we introduce some infections, and then they don't take off, they die out. If it's unstable, that means that the epidemic is going to take off. We're going to move away from this disease-free equilibrium. So how do we look at stability? Well, the first thing we need to do is look at our Jacobian. So in this case, the Jacobian, we take the partial derivative of the first function with respect to the first variable. So in this case, this is ds dt. Take the partial of that with respect to s. So we have minus a minus kb I over n. Do the same, but now for the second variable I. So we have minus a minus kb s over n. In the second row, we take the second function, so di dt, take the partial of that with respect to our first variable s. So there is just going to be kb I over n. And then lastly, our second function, di dt, partial derivative of that with respect to our second variable I. So kb s over n minus c. So that's our general Jacobian. Remember, if we want to look at the stability at a particular fixed point of equilibrium, we need to substitute in that equilibrium into our Jacobian. So we want to look at this Jacobian when s is n and I is 0. So we're going to have minus a here. I is 0, so the second term is just 0. Then in the top right, we're going to have minus a minus kb s over n. S is n, so n over n is 1. So we just have minus kb. The bottom left, our I is 0, so we end up with 0 here. And here we have kb minus c in the bottom right. Now, because this matrix is in upper triangular form, we already know what our eigenvalues are. We can just read them off straight away. We have eigenvalues of minus a and kb minus c. So we say lambda 1 is equal to minus a, lambda 2 is equal to kb minus c. Now, for this to be unstable, we need to have either lambda 1 greater than 0 or lambda 2 greater than 0. lambda 1 is always going to be less than 0 because a is a positive parameter, and we've got minus a there. So we need this lambda 2, kb minus c to be greater than 0. So when does that happen? Well, we just have a simple inequality here. So we have lambda 2 greater than 0 when kb minus c is greater than 0. So kb has to be greater than c. We divide through by c now. We end up with kb over c has to be greater than 1. And this thing here is known as our basic reproduction number. This R0, basic reproduction number. And this is the most important quantity in mathematical epidemiology. Who's heard of R0 before this course? Okay, a few hands. So when R0 is greater than 1, our disease-free equilibrium is unstable, which means that our epidemic takes off. This basic reproduction number is saying essentially how many new infections are produced per infected individual in an otherwise susceptible population. So you take one person, put them into this room, see how many people they infect on average. Okay. If they infect more than one person on average, the number of infections is going to grow. If they infect less than one person on average, the number of infections is going to decay to 0. There's also something related to this called an RE, which is the effective R number, or sometimes it's called R of T. And these are telling you the number of infections at a given time. Okay, so not at the beginning, the 0 is corresponding to this beginning when everyone's susceptible, but as an epidemic progresses, maybe more interested in the effective reproduction number at a particular point in time. Okay, so that was the key sort of points for disease models. Any questions on that before I move on to competition models? Nope. Okay. So today, we're not doing the same thing again. We're doing this one. Okay, so we're continuing our exploration of different types of nonlinear models. So we've looked at predator-prey models. We've looked at disease models just now and on Wednesday, and now we're going to look at competition models. So this is essentially an extension of the logistic model in one dimension. So you know the logistic model in one dimension. You have something like dn dt is equal to Rn times by 1 minus n over k. What this is really saying is that this term here, this minus n over k, saying that the growth rate of this population is being reduced by the number of individuals in that population. So essentially there's competition for resources within the population. This is known as intra-specific competition. Intra-specific competition. So as there are more and more individuals around, there's fewer resources, so the growth rate of the population decays. What we're going to do now is we're going to extend that to 2 species, where we still have, for each species, an intra-specific competition term. So this term in pink. But now we're also going to have this interspecific competition term. So this is interspecific. So that's between species. So intra is within species, inter is between species. What does this look like? Well, it's kind of similar to what we have when we have one species there. There's an n over k term. So our k's here are carrying capacities for species 1 and 2. So k1 is that in the absence of competition, how many individuals can we have in species 1, or k2, how many individuals can we have in species 2? So those are our carrying capacity terms on the bottom. And on the top, well, here, when we multiply this out, we're going to have our n1 is going to get multiplied by an n2 over k1. But we also have this alpha 1, 2 term here. And likewise, in the second case, we have this alpha 2, 1 term. What those alpha terms are telling us is the strength of competition between these species. Okay, so if alpha 1, 2 is equal to 1, then inter and intraspecific competition have the same strength. So if we have a rabbit competing with a sheep for grass, for example, if alpha 1, 2 is 1, that means that a sheep competing with a rabbit is the same as a rabbit competing with a rabbit. Okay. If, as is commonly the case, this alpha 1, 2 is less than 1, that means the competition between species is weaker than competition within species. And that's usually what you're going to find, something along those lines, because species will tend to separate into different ecological niches. Okay, so rabbits and sheep don't perfectly compete with each other. You tend to compete more with individuals that are more similar to you. Okay, so the more differences there are between them, the more you'd expect this alpha 1, 2 to decrease towards 0. You can also think of there being in here, in front of this N1, K1 term, you can think of there as being an alpha 1, 1, which is just equal to 1. And likewise here, we can have an alpha 2, 2, which is also equal to 1. Okay, so you can think of this there as being a coefficient in front of each of these terms, modifying how strong inter and intraspecific competition is. So the real question here is, can both species coexist, and when can they coexist? So let's have a go at finding our fixed points for this competition model. Let's have a vote. We live in a democracy. Hands up who wants me to go through this with you? Okay. And hands up who wants to do it by themselves? Okay. Well, you can race me. I'll go through it with you guys then. Okay. Maybe I should not have asked you guys. F1. All right, okay, I'm going to set these functions here. So we've got a competition model from above, but rather than having these general parameters, we've just substituted in some particular values for those parameters, okay? So the first thing I'm going to do is call these functions f and g, just for a bit of ease. We want to find our fixed points. So what do we have to do? Okay, if I'm going to do it, you guys have to contribute some vocally at least, okay? So what's the first thing I'm going to do to find my fixed points? Okay, a little bit louder this time, or not. I don't want to have to start picking on people, so we need to set our f and our g equal to 0, okay? So we find our equilibria by finding when our dn1 dt and our dn2 dt are equal to 0. That means there's no change in these populations, okay? So let's set dn1 dt equal to 0. What does that tell me? Well, for this to be equal to 0, either n1 has to equal 0 because of this term here, or the bit in the brackets has to equal 0. So we need 1 minus n1 over 3 minus n2 over 3 has to equal 0. So we can rearrange that. Let's just rearrange that now into n1 plus n2 is equal to 3. So we know that there's no change in species 1's population density when either there's no individuals in that population, and that kind of makes sense, right? If there's no individuals in that population, nothing can change. We also have this other condition here. There's no change in this population density of this species if the number of individuals, or this is population density. So you can think of this as being individuals per unit area. Okay, so maybe this is per acre or something like that. So if there are n1 plus n2 individuals equaling 3 in this given unit area, then there's no change in the population size of species 2. Okay, so let's think about if n1 is equal to 0, and dn2 dt is equal to 0. So I'm just taking this first value here, this n1 is equal to 0, and I'm substituting it into the second equation. So dn2 dt is equal to 0, and n1 is equal to 0. So this term here, I'm crossing out, is just going to be equal to 0. Note that when we're back, when one of these populations is equal to 0, we're just back into our classic logistic model. Okay, we know how to work out our logistic model. That tells me that either n2 is equal to 0 because of this term at the front, or the term in the brackets must equal 0. So 1 minus n2 over 2 equals 0. The second one here we can rearrange to be n2 is equal to 2. I'm just going to underline these things so we don't lose them. Okay, so that's one condition there. Let's think about the other one. So if n1 plus n2 is equal to 3, and again, we have dn2 dt is equal to 0. What do we have? Well, this is a little bit complicated now. We don't need it here. So we need to substitute this into our dn2 dt equation. So we're going to have 2n2 at the front, brackets 1 minus, I'm going to keep my n2s, and I'm going to eliminate my n1. So this 2 over 2 just cancels. So you have minus n1. If I rearrange, highlight it, if I rearrange this, I can get n2 is equal to 3 minus, sorry, n1 is equal to 3 minus n2. So we have a minus 3 minus n2. So I've just eliminated my n1 there. And this has to equal 0. So what does that tell me? Well, again, either the bit out the front must equal 0, so either n2 is equal to 0, in which case, if we go back to the thing in green, we know that n1 has to equal 3. Remember, we're substituting the green thing into our dn2 dt is equal to 0. So both of these conditions have to hold. So either n2 is equal to 0, in which case n1 is equal to 3, or the bit in the brackets has to equal 0. So we have 1 minus n2 over 2 minus 3 plus n2 is equal to 0. So let's rearrange this. We're going to have an n2 over 2 and a minus 2. So we're going to have n2 over 2 minus 2 is equal to 0. It implies that n2 is going to equal 4. Now, if n2 is equal to 4, what is n1 going to be? Did I hear someone say? -1. Okay, does that make sense? Right? It can't be -1. So what this is telling me that this is, while it's mathematically possible, it's not biologically realistic because we can't have negative population sizes. So not biologically. So this is really important because the mathematical model doesn't know that these are populations, right? It's perfectly reasonable for a mathematical model or for a mathematical system of equations to have positive and negative values. In the context of population sizes, negative values don't make sense. So when we're talking about equilibria of this model, we're focused on biologically realistic equilibria. And so that's not biologically realistic. So the only equilibria we have, let's go back and highlight these. We have n1 is equal to 0. In fact, I'll highlight it from here. If n1 is equal to 0, we either have n2 is equal to 0, in which case we have 0, 0 as an equilibrium, or n2 is equal to 2. So we have 0, 2. And then if we have n2 is equal to 0, n1 is equal to 3. Bless you. So we have 3 fixed points here of equilibria. So what do these actually mean? So 0, 0 means both species are extinct. 0, 2 means that species 1 is extinct and species 2 is at its carrying capacity. And 3, 0 means that species 1 is at its carrying capacity and species 2 is extinct. There's no coexistence equilibriums. There's no equilibrium where both of these species coexist. So we know that one of these will exclude the other, okay, because they can't coexist. Okay, so let's think about stability. So remember, we calculate our Jacobian. In this case, as this is a matrix of partial derivatives, I'm just going to write this down. It should be relatively straightforward, but we have 1 minus 2n1 over 3, minus n2 over 3, minus n1 over 3, 2n2, and 2 minus 2n2 minus 2n1. Hopefully I've not made a mistake there. If you're not comfortable yet with Jacobians, have a go at practicing that in your own time. So remember, we just take these equations here, this f and this g, we take our partial derivatives with respect to n1 and n2, and then put them in a matrix. So this is our general Jacobian. I'm going to call this J of n1 and n2. So to find the stability at each of our fixed points, we want to just substitute our n1, n2 values in that we found above, which I'll leave just there. So these values here. And then either read off our eigenvalues or calculate our trace and our determinant and then work out the stability from those. Okay, so let's think of 0, 0. We have J of 0, 0 is going to be 1, 0, 0, 2. This is in diagonal form, so we can read off our eigenvalues straight away. 1 and 2, they're both positive, which means that this is going to be an unstable node. It's an unstable node since, say, lambda 1 is equal to 1, lambda 2 is equal to 2, which is greater than 0. If I wanted to work this out by looking at my trace and determinant, I could. So if I look at my tau in this case, my trace, it's going to be 1 plus 2, it's greater than 0. My determinant is going to be 1 times by 2 minus 0, so 2, again greater than 0. Tau squared minus 4 delta. We have 3 squared, so we have 9, minus 4 delta, delta is 2, so minus 8, it's 1. So we have tau squared minus 4 delta is greater than 0, so we have real eigenvalues. We have a positive trace, a positive determinant. What does that mean? We have an unstable node. So you can work it out either way. You end up with the same answer. Okay, I want you guys to have a go at doing this for the other two equilibria. So at 0, 2 and 3, 0. You can either just read off the eigenvalues straight away, or you can do it by trace and determinant. If you do it one way and you finished, before I come back here, have a go at doing it the other way as well. Okay, let's see how you guys got on. So at 2, 0, your Jacobian is going to be, you have a 1 minus 0 minus 2/3. So you're going to have a third. N1 is 0, so this is 0 here. You're going to have 2n2, so that's 2 times by 2, which is 4. And then you're going to have 2 minus 2 times by n2. Again, n2 is 2, so that's 2 minus 4, it's minus 2. And then you're going to have a minus 0, so this is just a minus 2 here. Okay. A few people ask me, how do I know that I can just read off these as my eigenvalues? Okay. The reason being, if we imagine, I'm just going to zoom in up here. if we've got a general matrix like this, I'm going to do A, B, 0, D here. Okay, so we've got a matrix like this. It'll be the same if I had switched these around. If we want to calculate our characteristic equation for this, which is where we get our eigenvalues from, so if I call this matrix capital A, if I look at the determinant of A minus lambda I equal to 0, so remember from earlier in the course, this is our characteristic equation, this is where we get our eigenvalues from, then this is the same as having the determinant of little a minus lambda, b 0, and d minus lambda. And we're going to set that equal to 0. So if we calculate our determinant of this matrix, I end up with an a minus lambda times by a d minus lambda minus 0 times by b. Okay, 0 times by b. So this bit is just 0. And remember, we're setting the right-hand side equal to 0. So this is a quadratic, but it's already factored. So we know that either a minus lambda has to equal 0 or d minus lambda has to equal 0, which tells me that my eigenvalues are a and d. I should delete it, a and d, which were just these values here. Okay, so when you've got a 0 in the bottom left or in the top right, your eigenvalues are just the elements on the main diagonal, and this is why. Okay, so that was just a little aside. So here we have eigenvalues. Lambda 1 is a third, lambda 2 is minus 2. So we have lambda 2 is less than 0, lambda 1 is greater than 0. What do we have? Saddle. Okay. In the solutions, I'll upload what happens if you look at this by looking at the trace and the determinant instead, if you're more comfortable doing it that way. Both things give you the same answer. Okay, 3, 0. We're going to have, let's see, 1 minus 2 minus 0 up here. We have a minus 1, 0, and 2 minus 0 minus 6. We have minus 1, 0, minus 4. So here both of our eigenvalues are negative. This tells me we have a stable node. Now, show of hands, you got those? Okay. Okay, let's think about the phase plane and see what's actually going on here. So in this case, our null lines, if you've already calculated your equilibria, we've already done what we need to know for our null lines, right? If we go all the way back up here, we're setting dn1 dt equals to 0 and dn2 dt is equal to 0. That's already telling us our null lines, okay? So we can actually read them off from above. So dn1 dt is equal to 0 if n1 is equal to 0, or n1 plus n2 is equal to 3. So we can rewrite that as n2 is equal to 3 minus n1. So what do they look like? Well, n1 is equal to 0 is just going along this vertical axis here. In fact, I'll do it in a color. So that's one of my null lines. My other null line is n2 is equal to 3 minus n1. So that looks something like this. So it goes through this point here, 0, 3. And this point here, 3, 0. Because n1 plus n2 must equal 3 on that null line. Okay, and let's think about our second species, dn2 dt is equal to 0. We had either n2 is equal to 0, or we had 1 minus n2 over 2 minus n1 is equal to 0, which we can rearrange to be n2 is equal to 2 times by 1 minus n1. So what does that look like? Well, n2 is equal to 0 is just along this axis here. And the second one, n2 is equal to 2 times by 1 minus n1. We have a null line that looks like this. So this is the point 0, 2. This is point 1, 0. Here we have 0, 0. Now, if you remember, we only have equilibria when we have intersections between null lines, in this case, of different colors. Just put a little key on this. So the green and red ones intersect down here. So that's an equilibrium or a fixed point up here as well, and then at the origin. Guys, go a bit quiet, please. Thanks. Okay. I'll upload the solutions for the direction field, but in the interest of time here, I'll just draw them on. Have a go at calculating these in your own time. Like I said, the solutions will be online. If we find the direction field for this, we find that we cross this diagonal null line, we always go down. We go down as well here on this axis, above 0, 2, and we go up when we're below 0, 2. On the horizontal axis, we go right when we're to the left of 3, 0. We go left when we're to the right of 3, 0. And we cross this red null line, this diagonal one, going to the right. So what that means is, say we start here, in this bottom left triangle, we're going to be moving up and to the right. So we move up and to the right, we cross that null line going horizontally, and then we're moving down and to the right. So we move down and the right here. We start over here, up in this top region, we're moving down and to the right. So we end up moving down to the right, and we cross like this. Okay. Likewise here, we're moving down onto the left, so we move in something like this. So this is why we can see that this is a stable node. This is a saddle on the axis, because if we're just a little bit off that axis, we move away from it. But if we're on the axis, we move towards it. So this is a saddle. And 0, 0 is an unstable node. As soon as we move away from it in any direction, we move away from it. Good. It's an unstable node. Okay. So like I said, the solutions for the direction field are online. Have a go at working those out yourself. We see this case that wherever we start, as long as we're not on the axes, we're always going to end up with species 1 excluding species 2. And this is known as competitive exclusion. In an evolutionary sense, species 1 is outcompeting species 2, so it drives it to extinction. So it will win in that battle, if you like. Okay. For the last few minutes, I just want to think about other things that can happen here. So I am going to leave most of the problems here as exercises, because I think you guys could use the practice maybe in the nicest way possible. Okay, you guys, I often hear from students you want to have lots of problems to practice on. There are problems here with solutions. So I don't want to spend, I could have extended this into another lecture and we spend 4 lectures on this stuff. I think it's better if you spend some of your own time working through these things here as to how you actually calculate your fixed points, how you calculate your the stability at those fixed points, as well as then working out what those look like in terms of phase points. But I'll skip to this point here to think about what these different null line configurations might look like, okay? So above, we had a case that looked something like this in the top left, where we had a null line like this for species 1 and another one like this. In fact, they're always going to happen on the axes, so I'm just going to draw those in now. And then for species 2, we had something that looked like this. something that looked like this. So when our null lines were configured in this way, remember we just drew these trajectories, we always ended up going like this. This is a stable node for species 1, right? You'll see this when you calculate your direction field on these null lines. You cross that green one going down, the red one you go to the right. And if you start with positive values of species 1 and species 2, species 1 excludes species 2. Okay, that's not the only configuration we can have. Without loss of generality, we could configure them around the other way. So this green diagonal null line is below the red one. Again, we have a null line for species 2 along the horizontal axis as well in all of these cases. So if you calculate this, now that the red null line is above the green null line, the diagonal ones here, we end up moving in this direction now. So now we cross this way. And that means here that species 2 excludes species 1. So the orientation of their null lines will affect what the outcomes happen to be. How do I know those arrows are going that way? Well, when you calculate the direction field on this green diagonal null line, you move down when you're above the red null line, and you move up when you're below the red null line. So in this case, we're always above it. So these arrows on the green null line always move down. Here, the green null line is below the red null line, so we always move up. Okay, this becomes apparent when you work out the direction field. What are the other orientations we can have? One of them is if we have something like this, where our red null line looks like that, and our green null line now looks like this. In fact, I'm going to draw them a bit more extreme. Okay, so now they intersect in the positive quadrant, which means that we have 4 biologically realistic equilibria. So we didn't have this before in the 2 diagrams above, because they didn't intersect, those diagonal lines, they didn't intersect in the positive quadrant. Now they intersect here, which means that there is a coexistence equilibrium. But this isn't the only orientation we can have. We could have something that looks like this instead. Where we just switch those 2 around. I'm going to zoom in on these to make it a little bit easier. Okay, so what do we know from above? We know that when the green diagonal null line is above the red diagonal null line, we're moving down. So that means in this case, we're moving down here. And when the red diagonal null line is above the green diagonal null line, we move up. So that means we move up here. We can do the same over here. Here we're going to be moving down because the green diagonal null line is above the red diagonal null line. And in this bottom area here, we'll be moving up. Sorry, it's not very clear because it's quite small. We're moving up in that little triangle there. On the red null line, we move right when our red null line is below our green null line. And we move left when our red null line is above our green null line. So here. We apply the same over here. We move right when our red null line is below our green null line. And we move left when our red null line is above the green null line. Okay, so the directions on those null lines only depend on the relative positions of the green and the red ones, okay? So in some sense, you don't have to work these out each time. As soon as you know the orientation of those directions relative to the red and the green ones, we can just draw the arrows on. So what's the stability in this case? Well, if we start off here, I'll do it in a different color. If we start off here, we're moving up and to the left, and we do so until we reach this point here. If we start down here, it's not very clear. If we start in this tiny little bit here, we're going to be moving down and to the right, so we end up moving to here. Likewise, if we start over here, we'll end up moving down here. If we start up here, we end up moving down here. So what this tells us then is we have a stable node here. We also have a stable node here. And this should be an unstable node, if I remember rightly, in the middle. So coexistence is not stable in this case. If you move a tiny bit away from that coexistence equilibrium, either species 1 excludes species 2 or species 2 excludes species 1. In this case here, though, everything points towards the middle. And so we have this middle point here being a stable node. So what's the biological interpretation of that? It means coexistence, stable coexistence. If you perturb one of these species, if some of those individuals suddenly die out due to disease or something, they'll rebound and we end up back at this stable equilibrium. Whereas if you had some sort of perturbation in this case, you move away from it and one of those species is driven extinct.